Today's video is dedicated to Josie. We hope you're doing well, and we miss you. Ashley, stop crying. She'll be back soon. No, seriously, stop crying. Don't swear at me. Gosh, wow. Awkward moments. Okay. It's too bad that was caught on YouTube. It's like, wow, what do I have to put up with every day? Here we go. Graphing rational functions. We want to be able to graph functions where there is a, it's a fraction, like x plus 1 over x minus 3. Something like that. That's our goal. How do we graph rational functions? You've done it before. You know that rational functions generally have this structure where you have a vertical asymptote and a horizontal asymptote. Do you remember that shape? Yeah. But the graph that we're looking at, y equals 1 over x plus 2, that has a transformation. There's a shift. Do you recall what the shift is? Up to, down to, right to, left to. Do you remember which one? Which is it? If you notice here, the plus 3 is on the outside, so that's vertical. The plus 2 is on the inside, so that's horizontal. We better now? So I'm going to take this and simply shift it to the left 2 units. How's that? Not too bad, huh? All good? Okay. What's different about the next one? What does the squared do? When we square something, it makes it positive. So what's different is when it's squared, instead of them one being in the lower quadrant, one being in the upper quadrant, they're both going to be in the upper quadrant. That's what the parent function looks like. The parent function looks like this. I'll do it in blue. Vertical asymptote, horizontal asymptote, and they would both be in the upper quadrant. But the graph that we really want to sketch has some transformations to it. What are the transformations that you see? Yeah, the minus 3 brings it to the right 3 units. What does the negative do? Creates a vertical flip, so therefore the graph will look like this. You remember these, don't you? The next one, what's the shift going to be there? Up 3. No horizontal shift. And because it's not squared, it's going to be in opposite quadrants. We're going to skip this one right here. This one I have 2 different shifts. What are the 2 shifts? Up 2, right 3. You tell me something about the last one. Right 2 I heard. What else do I hear? Up 1. Like the way you guys think. Both want to go up because it's squared, but the negative will create a vertical flip. Every once in a while, you really need to pause, folks, and you need to look at what you did. And you need to say that this function right here, like, I mean, it's like, what the heck does that look like? But you were able to create a sketch in a matter of seconds, right? Like, if you can't find that somewhat impressive, I mean, come on. That's a good deal. That's a really good deal. Something I need you to focus on right now, and this is where we need to dig just a little bit deeper, okay? And this is the way that I thought of the functions. And so if I don't do a good job explaining this, I apologize. But I really am trying my best in this situation. I first want you to look at this function right here, okay? And if you notice the graph, I'm going to extend the graph even further. And I'm going to draw it here. I'm going to extend it even further. We always seem to focus on this part of the graph where something crazy happens, don't we? But the fact is, for most of the time, doesn't the graph just look like a line for most of the time? I mean, it's just, you know, moving along like a boring line, then all of a sudden, just something crazy happens, just like explodes at +3, right? Why does it disrupt like that at +3? Because +3 produces 0 in the denominator, right? When you get 0 in the denominator, crazy things happen. But otherwise, it looks like a horizontal line all the rest of the time, right? In fact, what horizontal line does it look like? It looks like y equals 2, right? I mean, it has a height of 2. It looks like y equals 2. Look at the next one. Basically, the entire time, it looks like a horizontal line. It just happens to blow up at an x value of 2. What horizontal line does it look like? It looks like y equals 1. See, that thing on the end is what it generally looks like. It just blows up at that value. Look at one more. Y equals 1 over x plus 3. The graph has a height of 3, y equals 3, for just about the entire graph. It just so happens that at 0, things blow up. But the graph wants to look like 3. That's what it wants to look like. You see that kind of reasoning? So let's see about this one. What makes that one different? That's what we want to dig into today. The others were review, but this is different. This is new. Why? There's an x on the top. And so what I'm going to do is just a little trick that you've learned in this unit. I'm going to take x plus 3, and I'm going to divide it into x plus 0. Do you remember how to do this? What do we multiply x by to get x? We multiply by 1, and we get x plus 3. Subtract. -3. So if I were to write this out, I would write it as 1 minus 3 over x plus 3. The remainder over the divisor. I have to pause. Is there any confusion how I got that? If there is, stop me. Thank you for asking. When we had something like this, say we had x minus 1 and we divided it into x squared plus 2x minus 4, okay? You would put the 1, and you go 1, 2, -4, correct? And time out. So I'm going to take this guy right here that I just divided. Where did you go? You're right here. Okay, and I got 1 minus 3 over x plus 3. If I just switch this just a little bit, and I go -3 over x plus 3 plus 1, all of a sudden, it's in a form that I know how to graph, don't I? What's the horizontal shift? Left 3, up 1. Is it going to be in the bottom and the top, or the top and the bottom? Top and bottom. Because of the negative, it creates a vertical flip. That's pretty good stuff, huh? So the first thing that we learned is that to graph rational functions, a lot of times you could just divide it to come up with the appropriate form. The second thing I want you to learn is this: identifying 4 really important characteristics. Number 1 is the horizontal asymptote, and number 2 is the vertical asymptote. The horizontal asymptote has an equation of x equals 1. What's the equation for the vertical asymptote? Oh, I'm sorry, I messed that up because I'm an idiot. Horizontal asymptote is y equals 1. What's the equation for the vertical asymptote? x equals -3. See how the graph wants to look like +1 the entire time? It just blows up at -3. There's two other parts that we're going to find. We're going to find the x-intercept, and we're going to find the y-intercept. Do you remember how we find the y-intercept of a graph? What do we plug in for what? The y-intercept happens when x is equal to 0. If you plug in 0 for x, you get 0 over 0 plus 3. What is 0 over 3? 0. Now I'm going to find the x-intercept. How do you find the x-intercept? Plug in 0 for y. 0 equals x over x plus 3. I'm going to show you a trick, okay? You want to solve that. Looks really complicated, right? I'm going to get rid of the denominator. You just multiply both sides by the denominator. What happens when you multiply by the denominator? You get 0 equals x. So when you're trying to find where a rational function is equal to 0, just look wherever the top is equal to 0, and that happens at 0. So what does that tell us? That tells us that we know one of the points it passes through. It passes through an x-intercept of 0 and a y-intercept of 0, and it helps us make a more accurate graph. We're going to try one more before I have you start one of the problems in your assignment. We're going to do this one, and we're going to start the same way. We're going to take x minus 1, and we're going to divide it into -x plus 4. What do you multiply x by to get -x? -1. Multiply back through, and I get -x plus 1. Excuse me, I'm sorry. Subtract. -x minus -x is 0, and 4 minus 1 is 3. So I would write this as -1 plus 3 over x minus 1. If I just switch it around, 3 over x minus 1 minus 1, now it's in a form that I know how to graph. Can somebody tell me about my shifts and transformations? Good. Down 1 and right 1 is what I heard. Now, before I actually sketch the graph, I'm going to show you how you can make just a little bit more of an accurate graph. I'm going to look at the horizontal asymptote and the vertical asymptote. Can somebody tell me the equation for the horizontal asymptote? Y equals -1. How about that vertical asymptote? Yeah, x equals 1, right? Now I want to do the x-intercept and the y-intercept. The y-intercept happens when x is equal to 0. If you plug in 0 for x, what do you get? Plug in 0 for x, what do you get? 4 over -1, -4. Good. Yep, -4. And in order to find the x-intercept, you just look at where the top is equal to 0. Where's the top equal to 0? 4. So if I plot 4 on the x-axis, and I plot -4 on the y-axis, that helps me as I draw my graph as it goes through those points. We're going to pause there. I'm going to have you do one of the problems on your worksheet. Here we go. The next one, this is, I forget to change this every year. It's a +3, not a +6. And I'm going to start by dividing. I'm going to take the x plus 2 and divide it into x squared minus 4x plus 3. What do you multiply x by to get x squared? X. Multiply that back through, and I get x squared plus 2x. Subtract. -4x minus 2x. Negative 6x, drop the 3. What do I multiply x by to get negative 6x? So negative 6, multiply through, negative 6x minus 12. Whoop. Put add, subtract. 3 minus negative 12 is 15. 15 is my remainder. So therefore, I have x minus 6 plus 15 over the divisor, or 15 over x plus 2 plus x minus 6. Are we all okay at this point? Okay, Jensen is smiling because he sees what's going to happen here. Okay? And what he sees is this. He sees that the end behavior, or this graph, wants to look like y equals 1, because that's what's sitting on the end. This graph here wants to look like y equals negative 1, because it's what's sitting on the end. So what does this graph want to look like? It wants to look like x minus 6. That's still a line. It's just a line with a slope, right? So instead of a horizontal asymptote, we have what we call a slant asymptote. Slope of 1 through negative 6. See how this first graph blows up at negative 3? So we have a vertical asymptote. This graph blows up at positive 1. We have a vertical asymptote. This graph will blow up at negative 2, vertical asymptote. So that helps give the structure of our graph. So in other words, we have a vertical asymptote of x equals negative 2. We have a horizontal asymptote. Actually, no, we don't have a horizontal asymptote. We have what we call a slant asymptote. And the slant asymptote is y equals x minus 6. There are two other things that I can find that would help me graph this. What are they? The x and y intercepts. How do we find the y-intercept? Plug in 0 for x, and we get 3 over 2. So I'll plot 3 halves on the y-axis. I know that that's a point that it goes through. I'm going to do one more. I now have to find the x-intercept. So if I want to find the x-intercepts, do I look at the top or the bottom? I look at the top. Where's the top equal to 0? Where is x squared minus 4x plus 3 equal to 0? How do I solve that? Factor, and you get x minus 3, x minus 1. So that means it goes through 1 and 3. There's the graph. I have more than that for the graph. You can see this one is in the top, not the bottom. How about the other side? Do you think it'll be in the top or bottom? Which one? Why? It's the bottom, but why? Got to have the right answer. It crosses the x-axis over here. Does it cross the x-axis over here? No. So if it doesn't cross the x-axis over here, then it's got to be in the bottom. And I know you're thinking to yourself, there must be an easier way to think this through or work through it. There is not. Some graphs are challenging. These are challenging graphs. And so that's the graph. I know it looks crazy, but we could show you a lot crazier graphs if you want to. We're going to do one more. I'm going to take 2x minus 4, and I'm going to divide it into x minus 2. What do you multiply 2x by to get x? 1/2. distribute that half back through, and you get x minus 2. Subtract, and you get, hey, wait a minute, there's no remainder. In fact, if you looked at it from the beginning, x minus 2 over 2x minus 4, you shouldn't be so surprised. That's the same as x minus 2 over 2 times x minus 2, right? When they cancel like that, you don't get a situation where it blows up. You get a hole. I know it sounds crazy, but that's actually what happens. I'm going to prove it to you in just a second. The graph wants to look like y equals 1/2. It's just a simple line. It says y equals 1/2. That's what I come out with. But we do know something crazy happens for an x value of 2. When it divides evenly, what happens? You just get a hole. I go back to that spot of 2. Just put a gap there. Now, your first natural instinct is like, there's no way that's a real thing. Not only is it real, I can show you on the graph, and furthermore, every time we take a derivative in calculus, it always involves a function that has a hole in it. Always. It's part of what makes calculus possible. And so if I go to my graph and I type in x minus 2 divided by 2x minus 4, notice that when I press zoom decimal so that every single tick mark is 1/10 of a unit, watch what happens with my graph. There it is. You press trace and you move over and you're like, okay, look at the x and y values. There they are. And when you get over to x equals 2, it just disappears. There are graphs that have gaps like that, and this is one of them. So if you would like to continue by doing the backside, you're going to discover some that have gaps and holes in them and others that have slant asymptotes. They're pretty cool, but I'm not requiring you to do so. I am requiring the first 4 problems. That's the end of chapter 3. It is my favorite chapter of first semester, but all good things have to come to an end.